Hey everyone, we're going to look at Achieve section 3.10, number 9. This is in the section on related rates. I've just recopied the problem from Achieve, and the numbers again might be a little different for the particular problem you have, but should be very similar. And there's a diagram they give with the problem. So a man of height 1.6 meters walks away from a 5-meter lamppost. So here's the lamppost. Here's my little stick figure man. They do a little bit better job with their man in the diagram. And this man is walking away from the post at a speed of 1.5 meters per second. Find the rate at which his shadow is increasing in length. So real important that you note that we're looking for the length, the rate at which his shadow is lengthening. That's important. And then we're going to give our answer to 3 decimal places. Okay. So I've recreated the diagram here, and I've added some variables to it, which you should do, right? Anytime we're going to start using a variable, X, Y, L, T, whatever, well, with the exception of T for time, you need to clearly define what that variable is. You need to state either in writing words or just labeling the diagram. And that's what I've done. So we're interested in the relating the variables of interest, and one variable is the length of the shadow. And so in my diagram, I've sort of filled in the shadow here, right? Everyone hopefully understands what's going to happen. The light's going to shine down, hit the top of his head, and all this will be blocked. So this will be his shadow right here. Notice I've called that L. So you need to clearly define what is the length of the shadow, okay? If you just start using the letter L and you don't have this diagram labeled, if you start, doing the problem, which I'll show you in a minute, with some letter L or Y, I don't know what it is. I'm not a mind reader, so you have to label your diagram. That's critical on these related rates problems. Clearly either label diagram or tell me, L is the length of the shadow. Okay. T we always use as time in these problems, so that's not a problem. The other quantity I need to label is the distance the man is from the pole. Why is that? Because I'm told that the man is walking away from the lamppost at a speed of 1.5 meters per second. So that distance from the man to the lamppost, which I'm calling X, we know the rate of change of that distance, right? In fact, the 1.5 meters per second, that is going to be the rate of change of X with respect to time, dx dt, right? There's the rate that we're given. And we're asked to find, of course, the rate that the shadow is changing, dl dt. In my problem, the man is 1.6 meters high, and the light pole is 5 meters high. So here's the picture. So what we need in order to proceed is to find an equation that relates X and L together, right? Then we'll do the calculus to find the derivative, the rate of change, and plug anything in. And so the way you're going to do that is by similar triangles. If you can tell, we've got a big triangle here with the lamppost all the way to the tip of the man's shadow and back again. That's a big shadow. We're, of course, assuming that this is 90-degree angle there, obviously. But then also the man with his shadow make a smaller but similar triangle, right? So this would be a right angle right there as well. And these two triangles are similar. What do we mean by similar? They have the same angles, right? Obviously, they both share this angle over here. They both have a 90-degree angle, and therefore this angle here and this angle here are the same. So they have the same angles, but obviously their side lengths are not the same. But remember, in similar triangles, side lengths are in proportion to one another. So I've drawn the big triangle here, right here. So the height was 5, and all the way was going to be what? X plus L together, right? The smaller triangle here, we've got height of 1.6 and then L. I folded my paper here because I did the whole problem. Instead of 1.6 here, I put 1.5. It's kind of easy to get kind of confused, so make sure you read the question carefully before proceeding to go through the problem. Okay, so what do we do with this information? Well, we're going to set up the following equation. Since the side lengths are in proportion, I know the length in the bigger triangle of X plus L, this base maybe we'll call it of this triangle, to its height. So the ratio X plus L to 5, that base to height, is the same as the ratio for the base to height of the smaller one, which is L to 1.6. This is what we mean by similar shapes, or in this case, in particular, similar triangles. So there's our related rates equation. Now, before you try and take any derivative in this case, it really makes sense to simplify. Okay, and the way I'm going to simplify is simply cross multiply 5 times L equals 1.6 times the quantity X plus L. I distribute that 1.6 through, right? And you can do that anytime you have a proportion like this, one fraction equal another fraction. Okay, it's the same as multiplying both sides by the least common denominator. And then I can subtract 1.6 L from both sides. 5L minus 1.6 L is 3.4 L. And then I can solve for L because remember I'm looking to find, if you recall, find dL dt here. So I can solve for L by dividing by 3.4. So it does help in this case to simplify. Usually I don't solve for one variable in terms of another variable all the time. I'll go right in and do the implicit differentiation with respect to t or time on both sides and work it that way. But this way it makes sense. Okay, so now I can differentiate, but clearly notice dL dt is just, this is a constant, 1.6 divided by 3.4. You can use your calculator to approximate that, but it's just a constant, times what? X, the derivative with respect to t of x, of course, will give us the related rates equation. So it's very simple, right? It's just, like y equals mx is just, a slope, really, right? Of course, times the rate of change of x with respect to time, which we know, right? dx dt we know is 1.5, so I can plug that in and I get approximately to 3 decimal places 0.706 meters per second. And it is positive, which is good because we would expect that to be positive since the shadow is indeed lengthening. Okay, now one thing maybe a little bit different from this related rates problems to others, a lot of times we're told to find a given rate and then we're told find it when, like, the man is 10 feet from the pole, or when the man is, or when the shadow's length is, 5 meters, or whatever the case may be. We're not given that. In fact, we don't need that information because notice in this relationship, the rates of change aren't dependent upon anything other than, right, the rates of change, right? There's no other variable in here. There's no X or L anywhere in here. In fact, it's a constant rate. dL dt is actually constant. The shadow is lengthening at this constant rate as long as the man is moving at that constant rate of 1.5 meters per second. I do a problem or have a problem like this in my practice homework. Very similar. You might want to try it. Instead of the length of the man's shadow, I talk about, I think I do it sort of in reverse. In other words, I think it's if the man's shadow is lengthening at a certain rate, what's his speed? So anyway, you might want to check it out, or it might be just like this one. Tell you the truth, I'm having trouble remembering exactly what that problem's like. Okay, I'll stop rambling. I hope this is helpful. If you've got questions, please let me know.